Yeah. Yeah. So workshop 1 p.m. on 2 p.m. So next week is the last workshop of the quarter. And the week after that, we have the competition where you're going to just present what you did and we'll choose the winners, give out the prizes. So we have 2 weeks. That being said, if you're just starting, I know at least two people that are just starting, I think. I think it's still very doable if you lock in. So today's workshop, what are we talking about? It's kind of a recap of everything that I've gone over in the last 4 workshops. Yes, last 4. So first off, what makes a good and easy AI? It needs, first off, an AI needs data, lots of data, and that data needs to be labeled. So the data should say what are the inputs, and then it should have the correct output. So if you're building an AI that looks at a picture of I don't know, a picture of a fruit, and it guesses what fruit is this, it needs both the picture of the fruit and it also needs a label saying this is a banana, this is an apple, this is an orange. So both the data and the labels together. And when you consider the data format, usually for an easy AI, I would consider numbers in, numbers out, or images in, numbers out. Those are generally the kinds of AIs that beginners should do, I think. And then you also have to consider, is your AI a regression or classification? So regression is choosing any number in a range. Classification is choosing a class or category. Class is how we call it technically, but you can also think of it as a category. So in terms of the picture of the fruit, that's classification. In terms of predicting the temperature, that's regression, because temperature can be any number, but fruit is one of several distinct categories. Once you have that, you should split your data into training data and testing data. So training data is the data that your model learns from, right? And it looks at the data, it compares, it makes a random guess at first, then it slightly improves by a tiny little percentage, and then over time it gets better and better. And then to check that your model actually works on like data it hasn't trained on, you have testing data. Because sometimes what it does is it will memorize basically the training data, and that's called overfitting. So you can see an example here, overfitting on the right, where it kind of just goes perfectly for every single point. But if there's like a new point added where the actual line is, then it might not actually put it correctly. It might not classify it correctly. It might not, because I would put it correctly. All right. Once you've got it in code, you want to actually load the data. So eventually you want your data to be all numbers, because AIs, it's all math. It's like multiplication, division, addition. It's all multiplication and addition basically. So you want to be turned into numbers, necessarily numbers instead of what's called a PyTorch tensor. That sounds complicated, but basically it's just a list or a list of lists in Python. If you've ever worked with kind of two-dimensional lists or three-dimensional lists even, right? Three-dimensional here meaning it's a list of lists. One-dimensional meaning it's just a list. As for how do you do that? How do you end up with a PyTorch tensor where all of your data is inside those lists? Well, you can use pandas to read CSV files. And CSV files are like your, sheets basically. If you have a sheet of data where it's like, all the numbers in and the numbers out. If you're using images, then you need to read the image file. And for that, I would recommend PIL, which is Python Image Library, or it's also called Pillow. And both of those will be able to read either CSV files or image files respectively. Then you can put them into a PyTorch tensor by just calling torch.tensor. I think it's literally like torch.tensor. And then you put in whatever data you have inside of here in Python. For example, if I'm just, my data is somehow only 3 data points, I would put 7, 5, 3. I wonder if I can put this up here. Ooh. Yeah, I don't know if that's super visible, but 753, then like I'm making here's my data points in a list, and then I turn them now into a tensor. And that's convenient because this is using Torch, or in other words, PyTorch. And PyTorch is how we're going to make the models because PyTorch just makes everything convenient for us and does everything in the background. So we don't have to do all this like complicated math. So that's all the database stuff is. You want to split your data, you want to be able to read your data, and then at the end you want to put it into PyTorch's format for data, which is called a tensor. And a tensor means it can be multidimensional. That's quick data processing speed run. Oh wait, data processing also is something you might want to consider. Depending on the format of your data, you might want to clean out values that are missing, values that don't show up that often, or unique values that kind of the distribution of different values, and maybe even rescaling values. So that's not always necessary. Specifically, we have this collab we sent out, I think, on week 2, which shows how you can do a bunch of these different data processing steps. I'm not sure why it always scrolls. Yeah, start at the top. Save a copy of this in Drive, and here we'll show you using the first one is using Pandas. So Pandas lets you read a CSV file, and then here it is. Here's the CSV file. Or and then you can make like graphs with it. You can like remove null values. You can remove duplicate values, stuff like that. And then if you're handling image data, I know a lot of people are doing image data, then you use PIL, and then you kind of just do something like image.open with the image path. And that's pretty simple. The only other thing you might want to do with images is, I don't have it here. Oh, wait. I'm kind of speed running all of this stuff because it's everything, and then we'll help you with your specific problems, I guess. So now that you have your data, how do we actually get this data and make predictions? What is our model like? So last week we kind of covered this, which is the structure of AI. How does it work? It's basically weights and biases, which are called parameters, and they determine the output. So at every one of these circles, so these are the inputs. Each of these circles you can think of as outputting a number. The first input layer is just whatever the input data is. So if you're predicting, let's say you have a data set of the weather. So you have, I don't know, humidity. What is stuff? Let's say humidity, pressure, I don't know, wind speed. And then you want to predict tomorrow's temperature. So I don't know, these are like 4 different numbers. I'm just writing them down randomly, but whatever. And it also has the temperature the next day. So this is 78 degrees. Let's say this one's 50 degrees, whatever, right? We have a bunch of data. How do we get an output from our inputs? Well, in this case, we have 3 inputs. So we would have 3 circles at our input layer. On this drawing on the board, I guess we have 4. At each of these hidden layers, what happens is these input numbers are multiplied and then added together. What are they multiplied by? They're multiplied by weights. So let's say we have 7, 8, and what do we put? Oh, wait, we had 7, 3, and 10, let's say. So we put in this data point in. And we wanted to predict that the temperature is 78 degrees because that's the right answer. Each of these lines means that it's getting multiplied by a weight. So let's say 7 here gets multiplied by -1. 7 here gets multiplied by 4. 7 here gets multiplied by 3. And then that goes into a circle up to how many ever you want. And each of these circles is called a perceptron, but it also takes in the other numbers too. And what it does is 7 times a certain weight, 3 times a certain weight, 10 times a certain weight. All those numbers get added together and then outputted. And all of these outputs can also go into their own perceptrons, which can go into a final perceptron. And basically that just means that every time as it goes, it gets multiplied by a weight, and each one gets multiplied by a different weight. So all that's happening basically is a bunch of random multiplications. Technically, if you guys know, multiplication is linear. That's why to make this nonlinear, because in general, most problems that we're trying to solve are nonlinear, we put activation functions after the perceptron. So that's kind of here and here. Right, if you see my mouse is right here and right here, we would put activation functions. And those are just some sort of non-linear function. Do I have a slide on that? No, I don't. So the most common activation function is just a non-linear function. Well, it's just this function that isn't a straight line. So this works. It's called a ReLU. If it's below 0, it outputs 0. And if it's above 0, so this is basically the x-axis. And I guess this is the y-axis. If it's above 0, it just outputs the same number. So if I input 7 into ReLU, it will output 7. If I input 3, it will output 3. If I input 10, it will output 10. But if I input -3, it will output 0. If I input -4, it will output 0. That's technically a nonlinear function, so we can put it in and it'll just add a nonlinearity. Yeah. And so now what we have is you can take a bunch of these inputs, put them in here, they'll get multiplied by a bunch of stuff, they'll get put through the activation function, they'll get multiplied by stuff, they'll get put through the activation function, and a bunch of stuff will come out. What it's multiplied by is the weights. The thing is, at the start, our weights are set randomly, so it's going to output something completely random. How do we decide these weights so that it multiplies them by the right things? That's the training loop. So suppose we have our data set here with the weather, we have the inputs, and we have the correct output. So what we would do is we would input our inputs here, 7, 3, 10, let's say, and we get an output. And because it's basically doing random multiplications at each step, the output is pretty much random. Let's say it just outputs, I don't know, 5. Completely random number. And what we do then is we compare this 5 and this 78. We say 5 is wrong, that's bad. It shouldn't be 5, it should be 78. So we compare how far away 5 is from 78, and we slightly change these numbers, the weights inside of our neural network, to get 5 slightly closer to 78. Very tiny amount, 1% better maybe. And as you do that for the next one, this one, you get a different random number for here. Let's say here you get 100. You move 100, there's slightly closer to 50. You do that over thousands and thousands of data points, and eventually it can actually predict the temperature accurately. In terms of code, how do you do that? Well, that's in a training loop and a testing loop. I should fix this to not say loop because it's not a loop. In training, that's exactly what it does. The first thing is it gets a prediction from the data. So you input something and you get a prediction in your model. Second, you score the prediction. So that's what's called loss. Loss measures how bad your model did. So let's say the actual answer was 15 and you outputted 5, then maybe your loss is 10. Depends on how you're scoring it, and you can score it using different methods. And then you just take that loss and you try to minimize it using what's called an optimizer. So the optimizer will update the weights to decrease the loss. And you do that thousands of times, well, at least hundreds of times. And eventually the loss will decrease and it actually will be able to recognize data points here and output something correctly. But the question is, okay, it's able to recognize the data points in your data set. What if we wanted to work on the real life, on stuff it hasn't seen before here? That's where we go into testing and see if it can work on real world data data that it hasn't seen before. So we have a testing phase after our training where we get a prediction of the model and we score the prediction. So we see how well does it do on stuff that it didn't train on. So that's very important that the stuff that's in testing is different data from the stuff that is in training. And that's what I talked about at the beginning, how you split your data into training and testing. From there, you can see, did your model actually learn something? Was it able to generalize to data outside of what it was trained on? Any questions?
Yeah, I guess a question about the training or in general. So within the Jupyter notebooks, you have code examples showing how to create these training and testing plans, right?
In the Colab I showed you, or just you? What do you mean?
Colab you showed us.
I think there is.
Okay.
I mean, training a loop. When I say loop, it's literally like a for loop. I'm gonna get to like the code specifically. Actually, yeah, I do have here. So here it says for batch in data loader. So data loader here actually will like do something nice where it will load the data nicely.
So
yeah, I believe this is in our Discord. If not, I can send it again.
I will look for the Discord.
Oh, I just sent it again. All right, so that's pretty much the code, right? You first need to initialize the data. So get your data ready, read the data, split the data, training and testing. You then need to initialize the layers of your neural network and the activation of your neural network. So like the ReLU activation that you put in between. You need to create an optimizer. And for that, you don't have to create your own optimizer. PyTorch gives you one. And you need to create a function to calculate the loss. And PyTorch also gives you that. So pretty much the only hard part is actually initializing the data there because PyTorch will give you all the other ones for you. Then you need to write a training loop to make a prediction, calculate the loss, and update the parameters. Then you make a testing loop, or maybe not loop, but just testing phase, I guess, where it makes a prediction and it calculates the loss. Yeah, so to get more specific on this. So layers activation in it. Yeah, so how do you actually write this in terms of code? So in terms of code, you first want to make the model, or you first want to get your data, but data I kind of talked about, that's kind of what's in the collab. Once you're done with your data, you should make the model. To make the model, PyTorch lets you make a model like class. So you would, in Python, you don't necessarily know what a class is, but you just write class and then whatever you want to call it. My cool model or whatever. And this is how you create a class in Python. Class my cool model. Is this visible for you guys? Yeah, someone. The only difference is inside of these parentheses, you need to put. Oh man. And then dot. And then dot module, which I'm just gonna write this like kind of in a separate spot, but somewhere you would have to do import. Import porch dot nn as nn, but that will give you the import for nn dot module. But yeah, you've made your module class. You just have two functions to write in it. One of them is called init. With 2 underscores, and the only parameter would be self. You don't really know what classes are in Python, but basically init just means that it runs to initialize or to start everything or set everything up. So all you need to set up are the layers and stuff. So you can do self dot, and you have to initialize them with self dot and then the variable name. So if I want to make a variable called layer1, I would just do self dot layer1, and then whatever I want to store inside of that variable. And for layer 1, let's say I want to make a new layer. I just do the same thing where I do nn dot linear. So linear means it's the same kind of layer that I showed previously, like this. It's each of these is in PyTorch is called the linear layer. The hidden layers are and the output layer are each called the linear layer. And each one has an input and an output, or how many inputs and how many outputs, right? So in our case, let's say we have 3 inputs, we just put 3, and let's say we want 5 outputs, so we put 5. It's that simple. Then if you want to make a second layer, you do self.layer2 equals nn.linear. And notice that the first one had 3 inputs, and it has 5 outputs. So if this first layer has 5 outputs, 5 things coming out, then this one needs to accept 5 things going in. So it needs to have 5 inputs. It has to match the previous number of outputs. And then you can output however many you want, and so on. Until whatever your final layer is, and your final layer needs to output how many outputs you actually want to predict. So in the case of the temperature, I was predicting one number. What is tomorrow's temperature? So my final layer would have only one output. So I just put a 1 here. But let's say I wanted to predict tomorrow's temperature and tomorrow's wind speed. So that would be predicting 2 numbers. In that case, I'd be put 2 numbers on the output. If you're predicting categories, let's say you're predicting dog, let's say the fruit example, you're predicting if an image, what fruit is it? If it's a banana, an apple, or an orange. In that case, the number of outputs is the number of classes that you have. So if you're predicting banana, apple, orange, you'd have 3 outputs, and each of the outputs represents how confident the model is that it's that one. So it might output, 90% confident apple, 5% banana, 5% orange. So you need 3 outputs because you have 3 categories. If you have questions about that, you can just ask me, but it's usually just however many categories you have or however many numbers you're predicting. And then the only other thing that's in a model is the activation function. So you have to also do that initialize that with self.activation. Well, technically you don't have to initialize it here, but I like to do it. And that is called nn.relu if you're doing a relu activation function. Now, technically, you can use any nonlinear function, so you don't have to do relu, but I like to use relu. And relu by default will just apply it to every single number that you give it, so you don't need to specify how many inputs or outputs it has, because it just applies it to everything. Right, so there you go. You create a model. It has layers that have activation functions. You just need to write a prediction. To make a prediction, you write a function called forward. This one also just has the self parameter, but also has a new input called, technically whatever you want to call it. I guess you can call it input. And input is whatever you're putting into your model, right? So the 3 numbers, for example, for the temperature, a picture, if you're putting in a picture, maybe some sort of other data, any kind of data, really. Well, to get an input, what does the model do with the input, right? At first, the input goes into the first layer. Then the input goes through an activation. Then it goes through the next layer, an activation, next layer, activation, so on. So it's exactly the same way here, where you say, let's say out, or I don't know, what do we kind of call this? Like the data is here, and it's not yet out at the output, but it's like partially through when it's here. The number's been multiplied by a bunch of stuff, and it's been, I don't know, I'll just call it partial. And we just say that the partial, whatever the numbers are here, we take self.layer1, and we put in the input. So if you look on the slide, right, it's you take these input numbers and you put them through the first layer. And what's happening there is it's just getting multiplied by a bunch of weights and added together. And that result, so after putting input being put into layer 1, that result is stored in partial. So then we want to update partial again because we want to put it through the activation function because we want some sort of nonlinearity. So we call it activation. And we just pass it through, or sorry, not the input. Now we pass our output from the first layer called partial, and we pass it through the activation function, and we reassign it to partial. So in other words, now partial has the value stored after it's gone through the layer, after it's gone through an activation function, and now it would go through the second layer. So you do the same thing with self.layer2 and partial. Right? And you assign that into partial as well. And then so on, right? Until you get through all of your layers. And finally, you would return whatever it is whatever, I guess, output. At the end, maybe you'd call your variable output, you'd return it once it passes through every single layer. So there you go. You have a model. It can make predictions. Now we want to actually write the training loop. Now, usually it is a training loop, and we call every iteration an epoch. That's like the formal term. So you could just say for I in range. This is how you make a for loop in Python. And let's say you have 20 epochs. So you're looping 20 times. And every time what you do is you first make a prediction. So how do you make a prediction? Well, you put. Oh, wait, I forgot to do some of the initialization. There's one more initialization step. So in addition to initializing your model, you actually also want to initialize an optimizer and a loss function. So you would want to first, actually, well, you can initialize, this is the class, but you want to make an instance of this class. So you can just say model equals whatever you called it. In this case, I called it my cool model. All right, so this line of code just puts this model as an instance of this class, if you know how that works in Python. But basically that just means this is a model and this initialization has been run and you can call forward on it. But you also want to initialize the loss function, which will measure how badly your model is doing. So I usually call that loss_fn for a loss function. And then nn dot depending on which kind of loss function you have. So you can measure loss in a lot of different ways. I would recommend kind of Googling this yourself, but basically MSE loss is what I would recommend if you're measuring a number, like a regression. And if you're doing a classification, I would recommend what's called cross-entropy loss, because there's different ways you can measure how poorly your model is doing. There's different kinds of metrics you can think about. But one very common one is nn.msc loss. If you get to this step, just like ask a question at Discord or something. And then lastly, the optimizer. I forget what exactly it is. So I think it's like nn.optim.atom or something. So there's a lot of actually different optimizers too. But actually for you guys, I would almost always recommend to use atom optimizer. I think this is how you initialize it. The import might be slightly different, but I think it's nn.optim.atom or something like that. But you can just Google atom optimizer in PyTorch, and you should be able to find out how to make it and, optimizer and initialize it. So cool. Now you have a model that can make predictions, a loss function that will score those predictions, comparing them to like what it's supposed to be. and an optimizer that will update your model to decrease the loss. So now let's just create the loop that does that. So you just do for I in range, and then however many epochs you want to train your model for. So if you train for more epochs, it'll take longer, but it might produce a better model. Sometimes it makes a worse model. If it might start like memorizing the data, which is what I talked about with overfitting. But in general, more epochs, you'll train better. You want to first, every loop, you want to make a prediction. Okay, so we take our model. And what we do is we just put parentheses after the name and we put in the inputs. Right? And this will output a prediction. So model, we put in from our data set, let's say we read a CSV file or we read an image file, or image, most likely data is going to be many image files or many rows of the CSV, because really you're doing this kind of in parallel, rather than just doing it one at a time. You would make a prediction on this data, and boom, that's step one. That's it. That's one line of code. Next one is you calculate the loss. So you can just say loss equals, and then just a loss function, again, defined for you by PyTorch. And what the loss function does is it compares the predicted to what the actual value should be. So we know the predicted, right? We just got it. How do we know what the actual value is? Well, it should be recorded in our data set. So if you remember in our data set, we had, for example, the picture of the banana, and then we had the label that said, this is a banana, right? We had the weather data, and then we said, this was the temperature. So we know what the right answer is in our data set. So we tell the loss function to compare our prediction and whatever the output is in our data. So I'm just going to call that data out. So both in this case, data means it's from the data set. So we compare what does the data set say the output should be, and what does our model predict as the output. And likely at the start, these are completely different because our model is making a random prediction. And this loss will be very high because the model is doing very poorly. So the last step is we want to decrease this loss, and that's updating our weights. Now, this one is a bit more complicated. It has, for some reason, several lines of code, but you don't really, it's always luckily the same lines of code no matter how you make your model, basically, or at least for the sake of, definitely for your first model, it's always going to be the same, which is first you want to basically just tell Torch to do some background calculation. You want to do loss.backward. This will calculate the slope of the loss, which basically tells the optimizer what direction to decrease the weights. So it kind of guides the optimizer, how should I decrease the loss? And then you just do optimizer.step. And this will step the optimizer, which will actually automatically update the weights in the model to be slightly better. So optimizer.step after you do loss.backward. Finally, you have to reset the optimizer for the next iteration. So before every iteration, you have to reset it. And with that, you can do optimizer.0_grad. And these three lines of code are kind of like exact. So they're in the slides, in last week's slides, if you want to look at them. You can also Google them online. They're very common, or I can help you clear them. But yeah, that's pretty much it. You make a prediction from your model using the inputs. You compare that prediction to what your data set says the prediction should be, and you get a loss. And then you use that loss to guide the optimizer and update the weights in your model to make the model very slightly better and decrease the loss. This is literally, I've written out on this whiteboard, like, other than the data code, to like do the data processing and stuff, which is on the Colab, this is like code that will be pretty much fully functional for making a neural network, right? So it's not that complicated, but there are some like oddly specific things. The only other thing, the last thing is a testing loop. So you want to go through all your data and you want to test it, maybe not in the loop. And to do that, it's exactly the same thing. You make a prediction and you calculate the loss. These two lines of code are exactly the same, but don't put in the same data. Don't put in data in and data out. Put in like a separate kind of batch of data you hidden. Often it's called testing data. This is called training data. So keep a bit of the data separate, usually around 30% of your data. you keep it separate, and then you basically copy these lines of code and then only run it on that separate data, and then just print your loss to see if it's as good as it was in training. Yeah, that's a speed run of everything I've covered. We've got 10 minutes left, which is not that much time, but I'll be going around now to help you guys with your models. Your question?
How do you set up the software and whatnot? Do you need like specific software?
Not really. You should pip in. Do you have Python installed?
No.
No. Okay, so you'll need Python installed. Yeah. What system are you using?
Mac.
Mac. Okay, then yeah, Python solution would be pretty hard. Does it shape it? Do you have Homework?
No.
Well, still, I don't think.
I mean, in terms of like computer experience, I have like almost nothing.
Oh, okay.
So,
Do you have a terminal? Do you know what terminal is? When you search terminal, should be thing. Yeah, here.
If anyone has any questions,
I
I
think
can help.
Python.
so you need to
Yeah, I have just
from like the Python website. Or...
Yeah, Python. Yeah,
Oh,
I don't know.
That's how I've worked on it.
Yeah, that's the
Yeah. Wait. Actually, can you?
But you can put it in.
Are you going to be posting
Yeah, it should be. Okay, so that reminds me. Don't it still
Can you see that?
like 12 or like 15?
Okay.
There's no one. So it's directly into contact.
Just someone on Zoom.
If you go to the